Welcome to today's Research Pays Off. I'm going to hand it over to our speaker, Eyoab Zegeye from MnDOT to talk about his TSD project.
Thank you, Lauren. Thank you for the invitation and for this opportunity. Thank you all for joining. My name is Eyoab Zegeye. I work with the research group at MnDOT. Today, I would like to update you on MnDOT's experience with the use of this new technology called traffic speed deflectometer. So this is a relatively new technology, but many state DOTs have been evaluating it over the years. Some of them already implementing it for network level testing. So here at MnDOT, we joined the pool fund study for TSD in 2023. And since then, we've been collecting data in different roads, in Minnesota roads. And since then, we also have created several funded research projects, one of them by NRRA, another one by MnDOT. But we are also conducting internal investigation on this technology in order for us to build our own understanding and capacity with this technology so that we can help effectively our district material and soil engineers, but also to have meaningful conversation with other stakeholders, with our research partners, with manufacturers, with consultants. So today I will be speaking on the results from the internal investigations. Another thing, it's also important for us to know that not only the technology, but how to apply it in line or alignment with our needs and with our current practices. So main focus have been where and when to collect data, how to process the data, but most importantly, what to make of the results and how to integrate them with our payment management or project scoping efforts. So with that, before I go to my slides, let me quickly also acknowledge my co-investigator, Eleanor Smith. She was a student worker, has been working with us for almost 3 years. She's a data science background. She's been helping a lot with this. But also I would like also to the contribution of our MnDOT TSD working group. As you can see here listed, they are all from different backgrounds, from research, design, payment management, foundation. Also the MnDOT district materials and soil engineers who play a big role in selecting the routes we test, but also ultimately who are the ones that are going to use the information for their to support their decision-making processes. Finally, the MnDOT and the Office of Research for allowing us for supporting the studies and for for always encouraging us to look into innovative testing technologies. So I will keep, in the interest of time, I will keep, I'll try to keep it less technical as much as I can. If you have questions, please reach out to me during or after this conversation. But just for those who are not aware with what is TSD or the traffic speed deflectometer, TSD is a emerging new technology which is similar to FWD but very different at the same time, because it's a system for testing the structural capacity or the structural condition of our payments, but in a non-contact way. Unlike FWD, that you have to use geophones that are coupled with the payment during the testing, the TSD uses this an array of laser beams here under this survey, under this track here. It has it may have 12 or 10 or different numbers of lasers that are pointed toward the payment, and they are measuring the response of the payment to the loading transfer to the payment through this rear axle. So while you're traveling, they can measure the deformation or the speed of the deformation of your payment. Because they don't need to be in contact with the payment, then you can collect data while you're traveling even at highway speed. So the key advantages of this, it means you don't have any disruption to traffic. You don't need to close the lane, but you are also collecting continuously data. So you have huge amount of data continuously. You don't need to select where to test. And then you can cover large areas, and finally you also reduce the concerns for safety and budgets. So because of this, this is becoming a very important tool for state DOTs to start evaluating and possibly start using it with FWD and other testing technologies. So one key difference with FWD, for those who are familiar with FWD, the TSD does not measure directly the deflection of the pavement. What it measures is the velocities, vertical and horizontal. I am using my mouse just to indicate what I'm talking about. So if you don't see it, please let me know. So anyway, the TSD measures the velocities, and from the velocities we obtain the slope of the slope of this deflection. This is an ideal float. This is the function of a slope. This is an ideal, and as you can see here, I am showing the points where you measure deflection using the laser beams. This is an ideal thing. In reality, these measurements, they don't fall on this smooth function. They fall all over. So there are techniques that you need to do in order to fit the function, from which then you can integrate that function, the slope function, and come to calculate the deflection ball, what we use in engineering a lot of times. So as you can see, the deflection now is obtained from the integration of that slope. So this is important that I touch on it before I go to the slides, because this is one of the reasons that we are doing the study. So when you move from slope to deflection, there are a few things that happen that could go wrong, or that could be a source of an error. So so one thing, as I said before, this is not a smooth curve, so you need to fit it. So this is one source of error. The second, because we are dealing in asphalt, we're dealing with a viscoelastic material. The response comes a little bit later after the loading. So there is this viscoelasticity lag that I'm showing here. As you can see, there is a lag between when the loading happens and when the response came in. And why this is important? This is important because since you don't have now anymore a symmetrical deflection ball, we are forced to use more complex integration techniques that, again, there are another source of error. But most importantly, this last one, in order for us to solve this integration, we need to solve this boundary condition and solve for this C, constant of integration. The way we do it is basically we need to assign a known location far from the loading point where we assume the pavement is not anymore deforming, what we call the at-rest location, or XREF. But because the van is traveling and it has more than one axle, it's very difficult, and there is also vibration included. It's very difficult to determine this at-rest location properly. So what happens most of the times, we don't know exactly. So we use a fixed number, 3.6 meter, around 3 meter. So what happens if we don't take it correctly, if we don't get it correctly, what is the C, we may overestimate or underestimate the deflection ball. What I'm going to argue today also, the pavement structure, if you have stiffer pavement or softer pavement, they are going to affect that those results. What I mean by that is that I'm trying with the results today. We are questioning, is it valid to use the same fixed reference point for all pavements? So with that, some of the objectives that we were trying to accomplish through the study were, first of all, understanding the influence of pavement structures and defining thresholds for critical response so that we can differentiate between good performing roads and bad performing roads. The other also is selecting appropriate data processing techniques and providing meaningful interpretation. we are not necessarily doing a fundamental or pure research. What we're trying to do here is research implementation. So looking at available techniques and see how we can use them for our needs, for our data, and how can we then scale it up to analyze larger and larger number of TSD data. So, and we also touched on the data preparation procedures. What do we have to do before we start analyzing this data? Well, I will touch on the techniques for segmentation and gathering supporting information, adjusting load and temperature effects, and then some ways for automated techniques for identifying and removing outlier measurements. Finally, another important aspect of this is also how to manage and process very large volumes of data. Compared to FWD and other, we have very large volumes of data. So if you are looking not only to simply to use simple calculations, but if you are looking also at back calculations, this is something we need to start thinking, how do we analyze this large data, and how do we use them, how do we report them, where do we store them, all those sorts of questions. So finally, ultimately, the idea is to find parameters from the TSD data that we can integrate or implement in the payment management systems or use for project scoping efforts. So the data set that I'm going to use for this study was collected in 2023, and because this was the first time we were collecting TSD data, we purposely selected the routes so that we can cover different payment types. So we included flexible payments, composite payments, and rigid payments. This data was collected in 1 day and a half. It is around 300 miles of road. So for flexible, we had three different types of payments. So I am here using the terms used in MNDAT, but I will try to explain. So by the way, here I'm using HMA to refer to bituminous mixtures. So most of these roads have been there for 50 years, 80 years. They've been there before the SuperPav HMA. So most of them, with HMA, I am referring to all bituminous mixes, road mixes, or HMAs that have been placed in there, and over the years they have been received several treatments. So is not necessarily one type of bituminous material. It's all mixtures that have binder, asphalt binder. So here in the first, we have what we call the full depth bituminous HMA on subgrade. And then the more traditional is HMA over an aggregate base and a subgrade. Then here, what I'm calling payment with recycled payment base. So these are originally HMA, originally full depth bituminous or BAB binder of aggregate base, which over the years have been reclaimed. So a portion of the HMA and a portion of the aggregate base have been reclaimed and recompacted to create a new a new aggregate base, which contains also material from the old existing payment. And then on top of that, an asphalt overlay is placed. For semi-rigid, I'm referring to payments that have been built as concrete, and then when they reach their end of life, service life, they've been overlaid with HMA to extend their life. Finally, the rigid payments, which are just concrete. So we've used them here just to compare the deflection and slopes from these different payment types. But as you know, PCC, they require different modeling techniques, different analysis methods. So we will not necessarily be talking about the PCC a lot here. This is just for creating benchmark, at least to look at what the slopes and deflection looks like from these different payment types. So the data preparation part. So after we collected the data, we started segmenting the data into homogeneous segments, what we call here D records. So basically into segments which have similar geometry, structures, and similar history. And I must say, because most of these roads have been there for 80 years, 50 years, 100 years. This one, for example, was originally built in 1922. It was a concrete pavement, which later became binder over concrete because it was overlaid with asphalt. But as you can see, over the years, they receive many treatments, and there is a lot of information out there. So gathering all this information and segmenting the 300 miles into homogeneous segment, it took a lot of effort, it took a lot of time. So this is something probably in future that we need to look at how to automate. So after doing this segmentation, we end up finding that 300 miles contained around 69 segments. We had few other more. We had around 72, but some of them, they were very small, just less than half of mile, so we didn't consider them. So we had 69 different segments from 5 different pavement structures. As you can see, the BAB was the higher representation. We had higher representation of BAB. Least was BCC. And here I'm showing here the different thicknesses of HMA in gray. And then here, for example, this is the one with reclaimed asphalt pavement base. Some of them we call FDR, full depth reclamation, or stabilized full depth reclamation. And then we have, this is the concrete one. And we have also the aggregate base that I need to find later. So the other thing to see is also how big of data samples we have here. For each of those, total we were looking at around 28,000 of data points of tests from 28,000 points. One other thing to say here is that we're looking at the data as it was reported to us from the vendor, in this case, the ARB system. So they already aggregated the data every 50 feet, every 15 meters. So this is already something which has been reduced in numbers. So even with that, we were looking at 28,000 of data to analyze. So the first thing we did was adjusting for load. This is the load on the right wheel loading during testing. The fluctuation was not that bad, but we wanted also to normalize the deflections. Again, the deflection, they were already the slopes, they were already converted to deflection by the ARB system. So we've been working only on the data that has been provided to us. So here we wanted to normalize the deflection to 40 kilonewton or 9,000 pounds, which is normally used. This is a standard loading system that we use for normalizing FWD and also TSD. It allows us to compare apple to apple deflection measured at the same loading. So this once we normalize that for this loading, we saw that we had around 15% reduction, but overall there was no big effect, huge effect of loading. On the contrary, as I will show a little bit later, the temperature had a huge effect. We had huge fluctuation in temperature. So when we try to see how to correct for temperature, we reviewed different techniques. One that we liked very much was the LTTP guide, which is on the FHAW website, is a guide for asphalt temperature prediction and correction. So this report has been there around for the last 30 years, if I'm not mistaken. But a lot of us knows this report for the Bell's equation. We have used Bell's equation to predict the temperature at mid depths for FWD analysis and other. So here we used it in this study, for example, for predicting the temperature at the mid depths, knowing the surface temperature and the air temperature. But what many people, including me, have not used a lot is the second part of the equation of the report, which is basically it has what they call delta regression equations. These are equations that have been developed using data from different testing facilities, including Mill Road, but others also in other parts of the state. So these are equations that they were developed to correct the deflections based on not only on the temperature, but also based on the thickness of the asphalt layer, based on the stiffness of the asphalt layer. Here, for example, they are using the latitude and the longitude, because those are surrogates for they tell us the PG grade, how stiff is your binder. So based on that, they are also in somehow accounting for the stiffness of the asphalt mixture, but they are also taking into account the strengths or the structural condition of the subgrade. So these were very, in my view, very sophisticated and complex equations. They have not, in my view, they have not been used a lot because they are very difficult to implement. I looked at the macro, Excel macro there, they are very difficult to implement. But if you take time and you understand them, they are very strong, and they do have some limitation, but good way, very effective way for correcting basins. The most important part of this regressions, they don't correct only one of the deflection. They don't correct only the deflection at the loading point. They correct the entire basin. So now I will show some example. So for example, here is the temperature fluctuation during the testing. As you see, early in the morning, this is something, and then late in the afternoon, there was a huge jump in temperature. It goes from 30 Celsius degree to around 20. So when you apply the technique for correcting the entire basin, here is, for example, if you take a data collected in at this point at almost close. So, and if you correct it to a reference temperature of 21, because there is no huge difference between the 20 during testing and the 21 reference temperature, as you can see, you almost have the same deflection basin. What happens if you take this is in another place? This is where you have the testing temperature was around 37, and then if you correct it for 21, there is a huge shift here. So what we did is we applied this technique to the whole to the entire data except for the PCC, and then we corrected the entire data. So as you can see here, there are areas they didn't need a lot of correction because they were collected. This is for example, here I'm zooming in only at the data coming from this segments here from, and as you can see, there are areas where you don't need a lot of correction, and there are other areas where the temperature correction was needed. So after that, we also try review different techniques for identifying and removing outlier measurements. So the method that we end up using and liked was the statistical method, the Z-score method for outlier detection. So if you use a sigma of 2.58, for example, this is the distribution of your data, what you're doing is you're identifying the measurements that are falling outside of the 99% of the data. So if your measurement is falling here beyond this 2.58, you're considering it as an outlier or flagging it as an outlier. The question becomes then which parameter to use. You can use the deflections, you can use some of the calculated empirical methods, but for example, when if we use the deflection, we don't have a clue of what those limits mean. So what we did was once we processed the data using all the analysis techniques that I will talk about later, we examined all the TSD parameters, try to see which of these they can be used as good metrics for identifying and removing outliers. What we found is that the subgrade modulus, or calculated or computed using the AASHTO 93, I will explain a little bit later, we found it to be an excellent metric. One, because it is, since this is the subgrade strength or the subgrade stiffness, is less sensitive to temperature and surface layer conditions. And the other thing also, we like the fact that it was here in the plot I'm showing, in the yellow ones are the ones that we flagged as outliers, and then using the z-score method, the black ones are the ones we are retaining. So what we found that the ones retained, they were falling very within what typically Minnesota subgrades between 7 and to 80 megapascals and 1 to 40 KSI, with 40 KSI being a very strong subgrade with crash stone and others. So it was falling inside. We knew what to make of these numbers, so we kind of liked the subgrade modulus metric. But then when we plotted the data on, because we have also the lat and longitude, we also liked even more the MR because it was, as you can see here, if you zoom in all these outliers, most of these outliers, not all of them, but most of these outliers, they were falling into known structural transition zones. For example, most of them, they were falling in bridges. They were detecting bridges. They were detecting exit or ramps, exit or ramp ins to bridges or transition to bridges. We found some of them, most of them, they were also falling in roundabout that are most of the times made of concrete. So we end up liking more the MR. So with this, we use the MR metric to basically, once if that value, that subgrade modulus was flagged as an outlier, we were removing the entire record associated with that MR value. So next, we moved, okay, now we start analyzing the data. So the first thing we did was looking at the shapes, at the magnitude and shapes, both of the slope and deflections. So as you can see here, I am plotting the slope on the left and the deflection on the right of data coming from the flexible pavements. What you see, for example, the BAB, which is the pavement with binder on aggregate base, and the reclaimed pavement base, which is the FDR and SFDR, they were quite similar. They were weaker than the full depths. If you have only asphalt layer on the subgrade, it seems like it's slightly on the slope stronger than. But then when you move from the slope to the deflection, the difference almost disappeared. So that's a question, where did that difference go? That's one question. But what we saw here is also the slopes were very clear. You reach the peak and then there is a quick drop, and then you have the deflection here. Somewhere here you will have the trace, right? But when we looked also at the steep, at the more stiffer pavements, the semi-rigid here, I am also having here the picture for you to remember which of these pavements refer to which. So what we saw is that, first of all, these are very rigid, so the deflection, the pavement had less deflection. That's what we expected. But what I didn't expect is to see this, you see here, once it reached the peak, it does not drop quickly like for the flexible pavements. It sort reaches a plateau. This makes me question then, is it going to reach the exact rest at the same time or at the same point as the other flexible pavement? But otherwise, you can see here there is a huge difference between flexible and rigid pavement only by looking at the slope and deflection curves. We also looked at the variability of the measurements, the CV, at each of these sensor points. What we saw is that when you go, what we saw is that one thing we saw is that the variability, especially close to the loading point on the slopes, were almost double, much higher than the variabilities in the deflections. So this, for me, raises a question: where did that variability go? So that's although not a big difference here, it does show me that some variability has been, it almost improved my measurements here. So is it something to take into consideration, and maybe something that we would like to bring to the industry and ask more questions? With regard to the variability, by the way, when you far from the loading point, they diminished. The variability were higher, spiked close to the loading point. When you look at the pavement, we saw that the PCC and the BOC, these are pavement with concrete, they had higher variability. And one reason for this is that we didn't necessarily differentiate between where the data was collected. Some of this data may be collected close to the joints, some other was collected far from the joints. So the fact that the concrete has joints, regular joints, that might have contributed to this higher variability. What I liked or was surprised was also the lowest variability was seen on what we call here the recycled pavement base, which is FDR, SFDR. And here, this type of pavement have the lowest variability in the data. In my thinking, this is because probably when you are stabilizing the aggregate base by using an old existing pavement which has still some binder, probably you are creating a uniform platform, a more structurally more uniform platform. So that kind, in my view, that's how I'm explaining it. So now I will start talking about the results after they have been analyzed using the different techniques. So just for us to, excuse me, just to make more sense of how we present the data, we also reviewed. This is one way also of looking at the data. We use the data using normal distribution plots and see what percentiles we can use as thresholds. For example, here, after reviewing different papers, we saw that the 85th percentile and the 15 percentiles are used to define the boundary where your pavement is performing poorly or performing very well. So if you are, for example, you're looking at deflections, if your deflections, here I am showing the ACI, are showing numbers higher than this 85 percentile, in this case around 110, then your pavement is very weak. It has high deflections. On the contrary, if it has less than the 15 percentile, it's strong performance. So, but when we're looking at for example, a layer moduli, this is the vice versa. When you have a layer moduli higher than 85 percentile, that's stronger. But here, so keep that in mind. But as you can see, even by plotting all this normal distribution, you can see that the pavement type affects the distribution. So this is, you cannot have the same threshold for all types of pavements. You can require that all your pavement have the same threshold, but maybe very difficult to achieve. So you cannot expect a pavement, for example, a BAB pavement to perform as strongly as a BOC pavement. So the first technique that we use is the deflection basin indices. These are very common, popular. They have been used in FWD analysis. Here I'm saying here these are simple computation, simple geometrical computation. So they are based on the analysis of the deflection curve of or basin bowl, deflection bowl basins of the deflection. So what you see, the most common are the ACI, the surface curvature index. That's the difference between the deflection at the loading point or the maximum deflection and the deflection at 12 inch or 300 millimeter. And then you have the BDI, the base damage index, and then the BCI. What we know is that the farthest you go from the loading point, your metric is less sensitive to temperature or to the stiffness of the asphalt layer. So the ACI is most of the time used for the top asphalt layer, and then the BDI, BCI are more associated, more frequently associated with the under and with the unbound aggregate bases and the subgrades. So this is a picture just to show you how the different deflection are associated to different layers or to different stress zones of the pavement. So here are some results. When you use these metrics, which are very simple to calculate, the ACI, BDI, BCI, one thing you notice, for example, all of them say the same thing in the sense the BOC was the strongest, and then you have the BFD, which is, here I have the pictures. The BFD is the full depth bituminous, and then the less stronger is the pavement with recycled recycled asphalt pavement, which is the FDR, SFDR. As you can see, some of these differences are significant, considerable. I am showing here, I'm plotting the median and also the 15th and the 85 percentile. So clearly, what we saw is that these metrics, they clearly identify the different pavement structures, and they have different values for different pavement sections. Some of them significantly or statistically even different. Then we looked at the structural number. The structural number, I am saying here, this is an intermediate computation. It is more involved. This is a technique that was developed based on data collected. This is data collected in the AASHTO road in the 50s. So these are, sometimes we forget to mention, these are empirical equations. So, and for those who are not familiar with it, the structural number they are associated with this AASHTO 93 pavement design equation. So this equation, it was basically an empirical equation which relates the anticipated traffic or volume or traffic volume to the structural capacity of the pavement, to the subgrade strength of the subgrade, to the strength of the subgrade, and to the functionality or serviceability of the pavement that is required. So you can do forward analysis of this equation. If you do forward analysis of the equation, that means you know the structural number. In this case, is the effective structural number and the subgrade modulus, and you can calculate directly the anticipated pavement traffic capacity easels. So which can be then turned to remaining service to the remaining or to the life or residual life of the pavement. So this structural number this effective structural number can be determined from TSD or FWD. Otherwise, you can do the inverse analysis. So if you know your desired pavement design level easels, you can back calculate and get the required structural number from this equation. So there are the effective structural number, which are determined from that, which can be determined from TSD or FWD, or the required structural number that is coming from this equation. Most of you are familiar with the required structural number because it's also used for design purposes to design the thicknesses of layers using this equation here. So the AASHTO 93 also provide these equations for calculating the structural number, effective structural number. And these are very, that's why I'm saying intermediate computation. They are a little bit more involved. They require iterative calculations. And then from these calculations, you can obtain the effective structural number, the modulus of the pavement, the entire pavement, all the layers above the subgrade, and the subgrade resilient modulus MR. So when we then after processing the data, when we plot these results, we saw quickly that again, the order was quite similar. You have the BOC, the strongest, and then the RPB, the lowest. We saw that the subgrade modulus on the BOC was also stronger than the others. Is it because the subgrade is stronger, or because the concrete the concrete on top of the subgrade is not allowing enough deflection in the subgrade, so for us to measure the real condition of the MR? But regardless, this was quite what we expected. Again, the pavement system was also lined up in this way. What we saw, the numbers, subgrade modulus numbers, were on the softer side. And this could be because most of the times our pavements have been there for 50, 80 years. So not necessarily, probably the subgrade is soft, or it was soft from the beginning, or over the years have softened a lot. But when we start also plotting at this effective and required structural number, there it was mixed. So first of all, most of the effective structural number was most of the time much larger than the traditional 5, which tells us this is a good ideal new payment. So when you see numbers than larger than 5, then the question becomes, what do I do with that? What is it telling me about my payment? Are my payments over designed? It could be the case. But in general, we also didn't like the fact that it was not distinguishing clearly between the different payment sections. So this is also, we kept questioning this equation. And then we also looked at how this equation can be, for example, used to calculate the remaining service life, so the easels. What we saw is that this equation is highly sensitive to the structural number and to MRB, to the subgrade modulus, because this subgrade modulus and structural number, they are used in their log version. And then when we reviewed the AASHTO and all the publication, the books on this equation was designed for subgrade modulus that has already around 3000 psi, 20 megapascal, and structural numbers less than 5. When you use it for highway payments like we did here, it basically then it start giving you very unrealistic number, because our subgrade modulus were much higher than 20 megapascal. They were on the range of 100. Our structural numbers that were much higher than 5. So these questions, I think, this is the question again that we would like to bring to the industry, but our view is that the structural number as it is not necessarily a good technique for processing TSD data or from highway payments, maybe for low volume roads. So then next we did back calculation. This is very complex computation. So what we did for back calculation, we adopted a software that was previously created for analysis of FWD data through a collaboration between University of Minnesota and MNDAT. We have published a paper on it, several papers, but last year we have also review its application for TSD data. So you can refer to that paper, but I will quickly tell the main features of this software. So this software is, in my view, very slick because it can be used for batch processing. What you do is basically you bring all your deflections, TSD deflections in a file, and then their payment geometry, layer thicknesses, traffic data, temperatures, and you put it in the software. Once you put it in the software, you basically, it does all the calculations for you. So what it does, what calculation it does? The first thing it back calculates the layer modelly based on embedded synthetic database, deflection database that are embedded in the software. And then it applies temperature and moisture correction based on the database of temperature history from Minnesota. And it adjusts the layer modelly for 5 different seasons, which are then used to calculate critical response of payment, the strain at the bottom of the asphalt pavement, and the compressive stress at the subgrade layers. This is all done automatically because the software has embedded finite elements analysis mid-layer that allows for all this calculation to happen automatically and seamlessly. Then finally, it uses these damage equations to calculate the damage indices, the fatigue for the asphalt layer, and the rating for the subgrade, and it outputs finally the tone. So all this is done automatically, and it takes about 7 seconds for 100 deflection ball. So all this data that I'm discussing was basically calculated in a regular computer for around in 20 minutes. So this was why we like. We are doing another. We are upgrading this technology, this software now. We have another contract with MSU, University of Michigan State University. We are upgrading this tone to add some features, but as it is also very, very strong. So we use this. Again, the current version of the tone software, it does not allow, it allows only for 3 layers. So we didn't in this, I'm not showing the result from Ph.D. because that software was not necessarily designed for 2 layers. So here I'm looking only at the 3 layers, BOC, BAB, and RPB. What we saw, it can calculate layer modelly. The layer modelly here I have also put the table. They were quite reasonable. One thing, maybe the concrete base, I would have expected a little much higher base layer modeling, but in general, they were basically confirming what we saw for the others. They do distinguish between the materials and between the pavement type, and they have also, they say almost the same thing. One important thing that came out from this study is when you look at the subgrade modulus calculated from this finite element analysis and the one from the AASHTO MR, we found out that the AASHTO MR is 40% larger than what we get from the finite element analysis. So this means that the AASHTO subgrade is overestimating the subgrade conditions. And then we looked at the damage, the fatigue damage on the AC layer and the rotting damage on the subgrade rotting. So what we saw from this analysis is that our pavement that have been there for this pavement considered in the study that have been like 50, 80 years, are more likely to fail due to failure in the subgrade, due to rotting in the subgrade than to fatigue cracking in the asphalt. This is because is all we expected it, because we do a lot of work on the top layer, because we don't, for budget concerns, we cannot not always reconstruct entire pavements. We do upgrade the top layers. So because of this, I think the results are demonstrating, confirming that our pavements are more likely to fail due to soft condition of the subgrade or subgrade rotting rather than fatigue cracking in the absence of any other distress modes, potholes and everything. If your main concerns are only fatigue and rotting, as it is, our pavements are more likely to fail to rotting than fatigue cracking. So we are over designing the top layer. We are doing very good job on the top layer. Of course, for budget concerns, the subgrade is what it is. So then we also looked at ways to calculate the remaining service life using the fatigue failure model. These are the fatigue model and the subgrade failure, rotting failure model. What we did is we looked at this equation relationship developed by Rada et al. In 2016. So basically, you don't need back calculation in this case. Once you have the ACI, the deflection basin index, you can come up with the critical strain, the strain at the lower, at the bottom asphalt layer and the asphalt layer modeling, and then which you can input this in the fatigue failure model. An easy way to do it. We also looked at the strains and the layer modulus calculated from the TON software. I just want to mention here the TON software does account for different seasons. So it has layer modeling in the fall, in the summer, and also in winter. What it means, in winter, if you use TON software, you're expecting less strains at the bottom of asphalt. In summer, you're the highest. So on average, the strain calculated from the TONs are lower, much smaller than the strains calculated, for example, by Rada, which was calculated only for one reference temperature. So when we look at this difference, we saw that they are very well correlated, but the numbers were very different because, again, the TON software here is assuming much smaller strains than the Rada. But in general, this shows that the concept of using remaining service life, once we calibrated our equation for our pavement, this is a viable way of doing it. Again, here I'm showing the strains calculated by the TON and the tensile strain calculated by the Rada equation here. They are very well correlated, but again, the Rada are much larger than the TON. Similar, the layer modeling from TON and the layer modeling from the Rada. So this confirms for us this is a viable way. Either you do it with using the ACI base, which is easy, then you don't have to do all the back calculation, or the base, the TON 2010. They tend to tell the same story, but the numbers are very different. Then we wanted also to explore relationship between the different metrics, the DBIs, the deflection basin indices, the back calculated indices, all of them. The reason for us we want to confirm is some of them are saying the same thing or not. We already saw that the structural number was giving us mixed numbers. We are questioning its application. So now we want also to compare it, for example, to the back-calculated, mechanistically back-calculated results and to see what they tell us. So here, then we examined all the data that was available for us, and we compared them one-to-one using linear and nonlinear correlations. Here, for example, I'm showing you some of them that showed very good correlation, and there were some that showed very bad correlation. So, and then we also divide them into categories. Those metrics that are simple to calculate, and then the metrics that may be coming from mechanistic-empirical back calculation, in this case, TON 2010 software. So all these results can be nicely summarized in a heat map like this. So here in the heat maps, I'm showing all on the y-axis, all the back calculated mechanistic properties, and on the x-axis, the Bayesian, the simple to calculate metrics. And here we have all the R's. Basically, we are measuring the goodness of that fit of the correlation. So if you have R squares larger than 0.5 here, I have flagged them for you to see. What we saw is that the slope or the deflection at the loading point, they were very well correlated with critical response in the pavement, both the tensile strain at the bottom of the AC and the subgrade. So the D0 was also correlated well with the damage indices that we calculate from the TON. Then we saw also that ACI, BDI, they were very well correlated with all the critical strains, not necessarily with the layer modeling. What caught my attention, this is the second time we're seeing it, most of the time we use the ACI as being the best metric for evaluating the top asphalt layer, but the BDI was showing more and more. This is we also looked at it in other data. It was showing more correlation to the damage indices in the AC and the RAT. But in general, the ACI and BDI seems to be very well correlated with all the response with mechanistic responses. On the contrary, the structural number, effective and required, they were poorly correlated to these mechanistically calculated properties. MR was very well calculated okay correlated to the subgrade. The deflection far from the loading at 60 inches was much better correlated to the subgrade stiffness. So the deflection far from the loading point, they are good metrics. They do give you good indication of how strong or how stiff your subgrade is. So this is a good heat map. So now, once we do to bring it all back, so what do we do with all this data? So here we have all the data that we calculated. They are 15s, 50, and 85 percentiles. And then we have summarized them in this. How do we use this information for network level planning or project level screening? So for example, based on what we saw, based on this information that I just showed on the slide, if we decided that the ACI is a metric that we would like to use for our network level evaluation, here we would go take the ACI and then all the, for example, the 85 percentile for us to flag good performing, bad performing roads. So if you, what I am showing here, we will have different threshold for the different payment types, BAB, RPB, PFD, and BOC. So then you can plot all your data. Each of these bars represent the data coming from each of the road segments that we analyzed. And here we flagged the road data, the data that have measurement more than 50% exceeding the 85% limit that I just showed you. So in this case, we found like 11 of these road segments, they were flagged as being poor performing roads. So we had several discussions with the project owners. They are further evaluating these roads now, but it does look like they match their observation. They were having some issues with these roads here. So this is for network level planning. For project level screening, what can you do with these thresholds? You can basically find the location where you have measurements above the 85 threshold, And this could be very useful. For example, in this case, I'm showing a 2 miles road, and there are these areas where we have them flagged because they had SCI larger than the 85 percentile threshold. So what does it tell me? This tells me that your problem is localized issues. So you don't, whatever these are problems, probably you need to take care of this location before you come up with a solution for that payment. On the contrary, in this other section, you can see the problem is not only localized, is extensive. Then probably in this case, it would be more budget friendly to basically repay, have the same treatment for that entire segment. So, we did also we tried to also see correlationship with distress indicators. We didn't see any correlation with measurement taken at the same time. But that's for another time. Some key takeaways. Payment structures significantly influence TSD results, in particular very rigid systems behave markedly different from flexible payment. There is strong agreement between TSD measurements, deflection basin indices, and mechanistic-empirical by calculated payment failures, except for the AASHTO 93 calculated structural numbers. So this is a question, are these structural numbers good for TSD or not? In our view, we don't think they are proper for that. And then we also showed how statistical thresholds can be effectively used for payment screening, both at network level and project levels. And then overall, the data indicate that payment in the study tend to have weaker subgrades compared to the upper layers, making them more susceptible to subgrade-related failures than other type of damage. What next? So since 2023, we have been working with our material engineers to identify routes that are good for testing. So in 2024, we collected 200 miles, 2025, 900 miles. Now we will apply what we learned on this road and basically increase our database. The threshold that we propose, they are statistical. So the more data we get, probably they will get closer to the true number, but definitely that database is going to change. This is going to be a dynamic thing, but at least this is what we are doing. The other thing that I would like to acknowledge, we do also have funded research projects looking at the accuracy, precision of the reliability and reliability of TSD measurement, but also another study to upgrade Mindaston 2010 software to add some viscoelasticity models in there to increase the number of layers, and also to include both TSD and FWD simulated synthetic database. So these are funded, one by NRRA with Professor Sohail Nazarian, and then one funded by Mindat directly with PI Syed Haider from SU. With that, thank you for the attention. I will leave the floor for any question you may have. Sorry. Lauren, the floor is yours. Oh, I do see. I see I have some questions on the. If Lauren, can you help me see? I don't know. I will go through. I don't know how we're doing with the time. So. So, for example, Bernard said, Bernard, do you want to articulate your question? I see. I'm looking at the. So here I see a question: why is 15 and 85 percentile for threshold? This is there is a good paper by the group in Italy, Professor Francesco Canestrari. So
that wasn't my question, Eyoab. That's not my question.
Sorry. Go ahead. Ask.
Yeah, I was wondering which of them, because I had a lot of comments.
Oh, okay. So choose one then, while Lauren takes control of it.
Okay. First of all,
I apologize. I'm here. My home internet died, and I've been trying to get back on. So I'm on my phone, but it's difficult to see everything. So maybe Eyoab, you could leave your screen, and then you can see the chat.
Okay.
We are at time, but if anybody wants to stay to get their questions answered, we can certainly keep going.
Okay, so I see the first one is the change in variability is due to integration of velocity to get deflection, irrespective of the boundary condition. It should be expected. Yes, it's not only one thing, it's different things that are happening. Yes, there is also that, like I said, there is a smoothness part getting the function, and then there is also the boundary condition solutions, and then the difficulty with getting the right boundary condition, because we are testing at high speed. You have the vibration, you have different loading points, not only the axle that we are using the less. So yes, I agree with that comment. Then Jocelyn, I wonder about the use of normal distribution on slide. Okay, gamma distribution, especially since there is necessarily lower bound for this variable, and bounded normal distribution might not be reasonable. We did see, you're right, on some of the metrics that we used, probably the normal distribution was not a good fit, but in general, in most of them, we saw that they were, we didn't do any statistical analysis to see if they were normally distributed. Most of them, they were kind of skewed one way or the other, but they were showing, I don't necessarily think they were far off from the normal distribution, but definitely we can look into that more. JP, I see here, George A, you have your hand raised?
Yeah, I will. It's more comments. I think you start by discarding outliers, and I can understand. Yeah, if you know there's a bridge, you need to remove that data. Mm-hmm. But we use outliers actually to pick up the weaker sections. So I wouldn't really discard the outliers right at the beginning. I will keep them through the analysis process, and then find out they might be telling you a lot. So that's a comment. The second comment is you find out that in some cases you don't match this velocity of the deflection very well, but then you match the deflections very well. Where most of other research that I've been looking at, if you match the deflections well, you tend to miss. If you match the velocities well, you tend to miss deflection and vice versa. And finally, my last comment, again, which has nothing to do with your work, is the equation that Gonzalo Rada developed to correlate SCI with strain. It's only valid for a very narrow range of asphalt thickness, because the same SCI for different asphalt thickness will give completely different strain. So you have to be careful when you use that. So yes. Those were my comments.
Yes, I thank you very much. These were very solid comments. I will start with the last one. Yeah, I also failed to mention the equation was developed by RADA, but then there was work done after that based on the RADA equation. I think Mahdi or Shrestha, they basically addressed that using simulation data. So they included much larger number of layer thicknesses and different configurations. So that equation, I mentioned RADA because that was developed by RADA, but then the constant of those equations that we used, sorry, I will take you back here if you see. This constants B, D, C, that with A, that they were created later, and they cover much a large number of layer thicknesses. So with that, I felt a little bit more comfortable because yes, at the beginning it was developed for main road, only unlimited, but then they extended it. Again, that is a simulated data. You're right, but that I want to make the point. With regard to outliers, yeah, that's something that we thought many times. We went back and forth. You're right. You don't want also to remove things that are actually bad for actually part of the payment. That's why we end up also plotting them on the geographical map just to see where they were falling. And then we also left it very loose. We were looking at the sigma 2.53. We were looking at data falling outside of the 99%. So very limited number. At the end, we ended up removing only less than 1%. But I agree with you. Yes, that's a difficult balance to find. You don't want to remove outliers. That measurements that are part of the study. I agree with you.
Thank you.
I think someone has. Priol? Yeah.
Yes, this is Prajol from Tensar.
Okay.
Like I have two questions, and I think you have already answered partially for the second one. For the first one, I'm just wondering, like when you were analyzing your TSD data, you were just correlating with MR and the structural number. But like in fact, like as we are also looking at this performance of the road, so when we are analyzing the TSD data within AASHTO 93 design framework, maybe we also need to look at the serviceability index that delta PSI. So what's your thought on that one?
Very good point. In this case, basically because our roads, they were all highway roads, they were mostly similar class. So in this case, I just use a fixed DPSI just to, yes, you're right. You could investigate it further by having different DPSIs, serviceability and functionality of those payments. But I wanted to focus more on the SN and the MR. So yes, I just use the same. They were all, especially this data set, we made sure that they were falling in the same route, they will have similar traffic levels, and then different similar history. So that's something we can extend to, but in this case we didn't. We just use the fixed DPSI. Okay,
that's great. So for the second one, there's a very small quick question. For the you already mentioned there is no correlation with TSD data and distress. So for the PCI, it won't be related. Have you also evaluated like if there is any kind of correlation between TSD data and IRI?
Yes. So I was going to show some data. So since you bring them, what we saw is that we looked at IRI. I was hiding the slide, so it's not showing, but I can show it quickly. Do you see my screen still?
Yeah, we can see.
So we looked at IRI. We have also what we call here RQI, PQI. So these are RQI, PQI. They don't take into account only the roughness of the payment, but also other function distress like the cracking numbers, the ratting. So we tried to get, and then we examined if there was any correlation with the TSD data. What we saw was, and these were collected in the same months, not necessarily the same time, but in the same months using a different system. What we saw, there was no correlation. But again, the thing is, we need to remember we should not even expect any correlation, because this is just a test in one time. What I would like, we're doing some investigation. If you collect TSD data and the IRI or roughness or cracking over the time, I would suspect that the payment that have bad structural condition, they will be failing faster than the ones that are in a strong structural condition. So we should not be looking into correlation 101, but we should look at the deterioration models.
Okay.
In my view.
Oh, that's great. Thank you very much for answering all those questions. Thank you.
Thank you. So then I have here comment from Katisha Summer, comment of the variability between deflection and slope. The lower variability of the deflection is mostly a mathematical artifact of the process of integration. I agree. Integration is weighted averaging, and the variability of DO is weighting averaging of all. Thank you. Again, Y15s and 85 percentile. There is a paper that I can refer you from Italy, Francesco Canestrari, Professor Francesco. They discussed a lot about why 85 is a good threshold, because 50%, the median, if you used, for example, the 50% median as a threshold, then you will be excluding or thinking that half of the measurements are bad. But 85% is a good balance between the number that you're seeing, but also if you want to suggest any repairs, 85, it does provide a good balance between economy and also the data that we're looking. So you can expand more on that paper, but that was basically taken from that study. Yeah, I can see here Andrea Graziani is here. Maybe he can add more comment to that.
Yes, just a little bit more. What you said is correct. This was basically like an engineering assumption. And yes, and it could be, yeah, it's not like written on stone. That's the point. It can be adjusted through time. As soon as you get more and more measurement, you can try to adjust this threshold, but okay, we believe that 85-15 could be a starting point, but again, they are not written on stone.
Thank you, Andrea. And then I see here, could this information be used in determination of the dates for placing and removing spring load restriction? Glenn, you're reading our mind. We are working on that. We're preparing on a project to exactly do that. Yes, it will mean that we'll need repeated testing, and then at least we're thinking of a pilot project, and then we'll see how it goes. But yes, it could be, in my view, it could be done. And then Proyel, I already addressed that. And then here, Gatiganti, why was the AASHTO 93 equation for effective structural number applied to traffic speed deflectometer, giving that TSD measure pavement response under moving loads rather than static loading condition? We used all the techniques that were available that have been used by others. There have been papers published on this. For us was reviewing them and then finding out if this is a good way or not. In our view, again, we found that this structural number equation is not was not designed or developed for highway payments, and also for, like you were saying, I don't necessarily agree with the dynamic part of it, because you're taking a snapshot, you're taking a deflection taken at one point, and then you are analyzing that deflection. So, but again, we agree on the fact that maybe it should not be used. Then segmentation data preparation stage is crucial for ensuring high quality, reliable process data. I agree. And it takes a lot of time. It took us around 4 months to look at all our history and then get back to that. And then I have Bernard. Bernard, do you want to, so that I can take a sip of water while, do you want to?
Yeah. Okay, yeah, I just said, unless we have moisture issues, subgrades transition from normally consolidated, should transition from normally consolidated deposits to over-consolidated deposits. Now, actual deflections from either from integration, that would be TSD, or otherwise, rather than moduli fitting, are more likely to capture these changes. I'm saying this in respect of changes that may occur in the subgrade, or things that will occur when we use some geogrid reinforcement. And there's always been that struggle to quantify that, either with TSD or with FWD. But if we know that deflections, whether the deflections are from integration or from direct measurement with the FWD, are more likely to capture those than fitting, because back calculation is just fitting curves. I think I don't know if you want to shed light on that. Is that a general observation you are making with the TSD?
It is part of that. I can also speak a little bit on that moisture thing. So, for example, in 300 miles that we have collected here, we've collected that data in 1.5 days.
Yes.
So this is one of the features why I think the TSD has an advantage over FWD. FWD, we would have used at least 12 weeks to collect that data on the 300 miles. That means we would have collected data on different moisture conditions, and it would have been very difficult to take out the contribution of moisture. With the TSD, we are still probably, like you write, there are also moisture conditions that are affecting the results, but in a way they are minimizing the effect of moisture differentiation because they are being done at almost the same condition. This is more true for temperature. Of course,
yes.
with moisture you may have water tables and everything, but at least we are minimizing the gap between the measurements in time and also in my view.
Sure. All right. Thank you.
With the integration part, I agree with you. There is, again, the contribution of the integration mathematical problem, but also the rigidness or the stiffness of the pavement. That's why I was trying to convey here. Very rigid pavements behave very differently from flexible pavements. So we should take into account that when we are integrating our deflections.
Yeah, thank you.
Thank you, Bernard. And then here, this has been answered. Rami, what was the season that TSD testing was conducted, resulting in the AASHTO 93 overestimating the subgrade modulus by 40%? Were you able to split the data by season and check how the comparison will look like? So this was a one-time measurement, Rami. It was done in September. And the overestimating is compared to back-calculated subgrade moduli. So I'm comparing the MR from AASHTO 93 compared to subgrade moduli, and the results show that the AASHTO 93 tends to overestimate the subgrade modulus. So we didn't split the data by season because we are looking only at the data collected in one day. I also wonder about the use, Jocelyn, I also wonder about the use of polynomial fits on slide 42. What would be model justification? It was not a polynomial fit. That was just there is no fit here. The results were reported to us by ARP, and we just connected the curves DOT. They were already integrated, and they were already, these were the results reported to us.
42.
Where I am here, I need drop meeting by Excel. Okay, Mahdi, nice presentation. The work clearly demonstrates practical implementation and use of data. However, please note that some of the analysis rely on several simplification, particularly in temperature correction and in estimation of metrics such as structural number, critical strain responses, and other related parameters. It would be beneficial to highlight these limitations and consider device-specific approaches, some of which are already available, while others may require further investigation. Great and significant. Thank you. Thank you, Mahdi. I agree with you. What we did here, look at the available techniques. Some of them have higher limitation than others. In the case of temperature, we like the temperature correction model because it corrects the entire basin and it looked, but there are again limitation with it. There is further investigation needed. I know you're working a lot on that. We have also Sohail working on similar things. So I agree with you. Thank you, Andrea. And then Yuma. Thank you, Yuma. And Summer, if you are here, I don't know if you want to add your comment, articulate your comment by yourself.
Which one?
Hello,
back calculation?
Yes, the back calculation, and then you have also survey providers could use the median instead. Oh, okay, if you can comment on that.
Okay, the first one is regarding the if you want to kind of remove the joint from the averaging, let's say, so that you can do like a K value and back calculation. My thought is like you can use a median instead of the average. If like the service provider provide you a median, that's not affected by the joint values. So then this way you'll get values that you can use directly.
Oh, I see. Instead of them aggregating it every 50 feet, they will just give us the median of that 50 feet.
Yeah.
Is that what you're saying? Okay.
Yeah. Kind of like the outliers are not, which is like the joints are not affecting the median.
Okay, so they will tend to remove the effect of the joints if you do the median.
Yeah.
Okay. Oh, thank you. Yeah, I was not aware of that. Any other comments, Samar?
I had something like when Bernard told you about the back calculation is just curve fitting. I was just gonna say I agree, and sometimes we give it more credit. It's not like than it deserves, or like more feels safe, but maybe it's not. We should not feel as it's still kind of just curve fitting basically. We should also be careful.
Yeah. So I'm here, Gatiganti. I wonder that sensor deflection data was used for. Data was used for? I wonder what sensor deflection data was used for the 19. So, that's a good question. Yeah. So I don't know if you are here, but here it is. What we did was we solved iteratively here. Basically, there is a process there is a procedure in the AASHTO 93, or I think Peter from ARP system also had a paper on that. So you can solve this equation, trying to find which sensor gives you the lowest MR. So it's an iterative way by running this many times for all the sensors and finding the sensor that provides the most critical, the smallest number of MR. So most of the times it's 36 inches, sometimes it's the 60-inch sensor. I hope I answered.
Yeah. That was my question. Yeah, I was basically trying to see if that's a soil, basically stress softening issue. Like if you're using the forest more sensor, potentially that's kind of like articulate or overestimating those modulus values if it's like a stress softening soil.
Okay.
But if you did try to process, yes, I mean that's kind of like at risk there. So my question was pretty much on that, because I know like a lot of people use the farmost sensor in FWD analysis, and they could probably start picking the wrong value what it's supposed to be, depending on the nature of the soil.
I see. Okay. So, but in our case, I think I don't have it on top of my mind. Most of the time was 36, 48, or 60 based on this iterative equation.
Yes, thank you.
We didn't hardcore it. We just solved this problem and then automatically find which one was. So thank you, Katiganti. And then I have Shrestha. What is the standard payment design practice, ME or empirical at Mindat? So the standard is we have MIMPAVE. MIMPAVE is our standard design procedure that was developed by Mindat way before ME, if I remember correctly. But we have also the TON 2010 software that I showed here, which is very aligned with MIMPAVE, and it's a mechanistic back calculation, which with results, for example, for the damage indices, which were calibrated on few limited test sections in Mill Road. So one of the reasons that we were looking very high, very low damage indices here is because that software was not necessarily calibrated for highway pavements. That's something we're doing on this new work. And the upgrade, we want to calibrate the software TON 2010 for highway pavements. I think then I hope I have addressed that. Thank you, Ali. Slide 25. What is the source of the data? Collected data model. Slide 25. I don't know if you are here. This is source. This is the same data. This is the data that we collected, and then I'm using the same data here for showing these results. Thank you. And then Angelo. The threshold may be a little bit conservative. What about 2575? Again, like Andrea said, yeah, they may be conservative. This is the first time we did it. It will, with time, the more we get the data, we will we'll try to see what works best. But I think we will also like to see, once we start implementing these thresholds, we will need to have a conversation with the material engineers saying, okay, it is too loose or too conservative, based also on the budget, what budget you have, and how you need to prioritize projects. Summer, okay, yes, yes, thank you for mentioning that. Has an equation that is thickness dependent. Yes, we use that one. And then George, thank you, Summer. Yeah, okay. Elihaj, thank you. Yes, it's recorded, is available. The presentation is available. It will be available on the NRRA websites, like Lauren said. Thank you. I think I have. If I have not addressed any, and if you are here, please ask questions. Lauren, the floor is yours. I feel like I have addressed most of them, if not all.
Okay. Okay, great. Yeah, thank you to everyone who has stayed till the end here. And I'm glad we were able to get through those questions. The recording will be available on YouTube by the end of the week. And we hope to see you next month for the next presentation. So thank you so much and have a great Tuesday.
I just want to add, Lauren, we have also submitted this paper for publication in TRR. If you are interested, I will send you the draft or the manuscript. So just want to add that. And thank you very much for your attention and for very engaged conversation. Thank you.
Yeah, I think I saw a hand raised.
Yes, I think Syed. Oh, I think.
Yeah, I couldn't see who it was. Okay, but we will sign up for today, and I hope everyone has a great rest of your day.
Thank you, Lauren, and thank you, everyone.
Thank you.